Welcome to the deep dive. Today, we're really getting into something cutting edge. It's about this constant need for speed in our world, right?
Absolutely. Faster data, smarter AI,
Hmm.
computation that feels, well, instant.
Exactly. And what's fascinating is how often the answer isn't just faster electricity, but actually using light.
Precisely. We're talking about silicon photonics,
Yeah.
or SIFE.
SIF, yeah. It's becoming really central for high-speed data, for AI computation, and designing these integrated optoelectronic chips.
And it's moving fast. We're
Yeah.
seeing it jump from the lab right into mass production, mass validation stages now,
Especially in areas like co-packaged optics, bringing light right onto the chip package.
right next to electronics, yeah. Huge speed boost. And things like LiDAR, too,
That laser sensing tech,
Yep.
crucial for autonomous driving.
and various other advanced sensors, yeah. It's spreading.
But here's the paradox, the really interesting bit. While this light-based tech is taking off,
The old tools are struggling.
yeah, the traditional equipment engineers use to find faults in electronic circuits. Machines like EMI.
Yeah, EMI detects those faint light emissions from failures, hot carrier luminescence, and OBERCH.
OBRCH uses a laser to heat things up and see resistance changes.
Exactly. They're great tools for finding, thermal hotspots or electrical anomalies. Standard stuff.
But they hit a wall with pure photonics.
They do. They're essentially blind to the critical photonic characteristics, things like the actual structure of the waveguide, how the resonators are behaving, optical loss.
You can't just see that with the old methods.
Nope. Imagine trying to diagnose a SIF chip when your tools only show half the picture. They just don't have the functions you need, like coupling light at specific wavelengths, measuring optical loss directly, or analyzing resonance frequency.
So that's our challenge for this deep dive. How do you diagnose problems in something that works so differently from what your tools were made for? We're going to explore how companies are strategically upgrading their existing EMI and OBRCH platforms, making them into these hybrid systems.
Not just small tweaks either. It's about bridging that critical testing gap for SIF components.
And it seems to boil down to three uh, key areas of modification, three main upgrades.
That's right. The first big one is an optical system adjustment, a pretty major overhaul.
Okay, so what does that involve? Swapping things out.
Yeah, basically swapping out the existing lenses and filters for new ones. These are specially coded for the key communication wavelengths, 1310 and 1550 nanometers.
The standard wavelengths for optical networks.
Exactly. And critically, they integrate a specialized camera, an NDAS camera, indium gallium arsenide,
Why that specific type?
because it can actually capture images in the near-infrared band. It lets engineers see the light moving through the silicon, which is, essential.
Right, you need to see the light itself.
And they're also adding things like a laser scanning module or maybe a variable wavelength light source. So you have precise control over the light going into the chip.
So it's really about giving the system the ability to, well, see and interact with light in this specific way. Must be tricky adapting optics like that.
Oh, absolutely. It's all about precision at those
Ah.
specific wavelengths, making sure the whole optical path is optimized for near infrared, which behaves differently than visible light.
Okay, so once you can see the light, what's next? You need to analyze what you're seeing, right?
Precisely.
Yeah.
And that brings us to the second area, a big data analysis function expansion.
Expanding the brain of the system, basically. What does that look like?
It means bringing in new modules, like wavelength scanning modules and power analyzers.
Okay.
And these tools allow for really precise measurements of key SIF components. Things like ring resonators,
Those tiny loops that filter light.
yeah, or Mach-Zehnder interferometers, MZIs, which are vital for modulating light signals.
So what can you measure then?
Well, this unlocks really critical stuff like optical component loss mapping, which sounds technical, but it's fundamental.
Knowing how much light you're losing.
Exactly. It's the difference between a smooth-running data center and one grinding to a halt because the signal's degrading.
Makes sense.
It also lets you observe phase shifts, track coupling efficiency really accurately. And here's the smart part.
What's that?
The upgraded system keeps the original EMI and OBRC functions.
Ah, so you don't lose the thermal and electrical analysis.
Exactly. You get what's called multimodal analysis. Thermal, electrical, and optical all analyzed together, often overlaid.
Wow, that's powerful. Like having thermal vision and X-ray vision at the same time for the chip.
It gives you a much more complete picture of what's failing and why.
Okay, that makes a lot of sense. But you mentioned mass production earlier. Getting things physically connected precisely and quickly is always a bottleneck, right?
It absolutely is.
Which leads us to the third upgrade, which sounds like a real game changer. the six-axis automatic loopback coupling module. Why is this so important?
This module is really what enables high-volume testing. It's basically an automated alignment platform with 6 axes of control,
Six axes, so not just up, down, left, right, forward, back.
but also rotation, pitch, yaw, and roll. Think incredibly fine, micro-level control in every possible direction and orientation.
And why do you need that much precision?
It's absolutely essential for connecting a special lensed fiber to the tiny input and output points on the SIF chip, specifically things called grating couplers.
That's how you get light efficiently into and out of the silicon.
Exactly. And the loopback part is clever. An optical fiber module automatically takes the light coming out of the chip and reflects it straight back to a power meter, or maybe the laser source itself.
Ah, so you don't need a second fiber to collect the output.
Precisely. It simplifies the whole setup enormously for testing transmission characteristics of waveguides and resonators.
Clever. And it's automated.
Fully automated. There's a power sensing system that provides feedback for auto alignment and lets you do rapid batch testing. Huge speed increase over manual alignment.
So it's like a tiny robotic arm doing incredibly precise optical connections super fast.
That's a good way to think of it. Yeah.
So with all these upgrades, the new camera, the analysis tools, this robotic coupling, what can these machines do now that they couldn't before? What new faults can they find?
Well, quite a lot, actually. The transformation really unlocks capabilities that were impossible before. For instance, you can now accurately measure the optical transmission loss in a waveguide using that loopback path.
Which just wasn't supported before.
Right. You can watch how a resonator's wavelength tuning changes by scanning the wavelength and using that real-time NJS imaging. Gives you direct insight into its performance.
Okay.
And remember those optical coupling defects, where the light isn't getting in or out properly?
Yeah, you said they might just look like a weird hotspot before.
Exactly. Now, you can overlay the infrared image showing the light path with the OBR-CH thermal map, and you get a complete diagnosis. You see where the light is going wrong and the resulting thermal effect. It tells you exactly what the problem is.
That's incredibly useful.
And testing chips with multiple optical ports, multi-port modules, that becomes truly practical because of the automated coupling and power measurement. That used to be a huge headache.
So the benefits seem, well, pretty significant then. This isn't just incremental improvement.
No, not at all. It's a major leap. Think about it. This kind of modular upgrade extends the life and boosts the value of millions of dollars worth of existing equipment.
Instead of buying brand new, dedicated photonic testers, which are very expensive.
Exactly. It brings these older platforms right into the modern optoelectronic era. And you get those multimodal capabilities, thermal, electrical, optical, all overlaid. That dramatically improves fault analysis accuracy and, frankly, the speed.
Finding problems faster means getting products developed faster.
Absolutely. Ultimately, this builds the foundation for offering completely new SIF testing services. Things like testing ring resonators right on the wafer, or detailed waveguide anomaly analysis. It accelerates the whole cycle.
It sounds like a very strategic way to adapt. And is there a clear path forward for rolling this out?
There is. The approach is quite methodical. First step is usually building a proof of concept, a POC platform.
Just to prove it works.
Right. Validate the concept against maybe one or two common SIF components like the ring resonators and MZIs we mentioned. This involves integrating the key parts. The NGS camera, the 6-axis stage, maybe a simple power monitor.
And if the POC is successful,
Then you can scale it up. Expand it into a proper mass production-oriented optical test station. You'd integrate things like probe cards for electrical contact, fiber arrays for multiple optical connections, making it suitable for high throughput.
channeling lots of chips quickly.
Exactly. And then the longer-term vision often involves collaboration, working with universities, research institutes, or maybe packaging and testing clients to push the technology towards full commercialization and get it widely adopted in the industry.
So connecting this back to the bigger picture, what's really striking is how you can take existing established technology
Yeah, these MEO Birch machines.
and with some really smart targeted upgrades, unlock completely new capabilities. You're essentially opening the door to these next-gen AI and optoelectronic markets.
It's a fantastic example of engineering ingenuity. Innovation isn't always about starting from zero.
Right. This deep dive really highlights how enhancing what we already have can be incredibly powerful. It gives companies a significant technical edge in this crucial SIF testing space, which, makes you wonder how many other legacy technologies out there might just be one clever upgrade away from becoming indispensable again. And how does understanding this constant push for precision in testing change how you view the almost magical speed of the technology we use every day? Something to think about.